Good evening, guys. We are going to do some online physics videos that are going to hopefully help supplement our Zoom time. So without any further ado, I'm going to jump right in. All right, just making sure we're recording. I already did this video twice, and one time I didn't hit record. Okay, here we go. All right, we're going to talk about lenses, and we're going to talk about how light travels through objects or not. So let's start by looking at a definition, and that is has to do with whether or not light can pass through an object. So an opaque object is an object through which light cannot pass. Okay, a table, a wall, right? Things that any object that light is not able to pass through was what we call an opaque object. A transparent object is an object through which light can pass. Okay, oops, get my pen up here. Let's change my color here. Let's do blue. All right, so a transparent object is an object through which light can pass. Now, light has an interesting phenomenon that happens when it travels through transparent objects. So as light crosses the boundary from one medium to another, the speed at which it travels changes. Now, from our last module, we learned that light travels more slowly through more dense matter. So the light travels more slowly, but the energy of the light, and therefore the frequency of the light, doesn't change. How do we know that? Well, let's look at this equation right here. Right? Energy equals Planck's constant times the frequency. We just said that the energy of the light is not changing. That would have to then mean that the frequency of the light is not changing. Because why? Well, because the h is a constant, it doesn't change as well. So if the energy is not changing and the frequency is not changing, then what is changing? Well, let's look at our equation for frequency to understand that a little bit. Okay, so we know that frequency equals v, which is the speed of light in whatever medium it's in. Last module, we were talking primarily about the speed of light in air, right? And we used 3.00 times 10 to the 8th meters per second. But that velocity, we know is different depending on the medium, right? So for mediums other than air, we would have a different value for the velocity. But what's important here to note is that if the velocity is changing because the medium has changed, then what has to change as well? Of course, the wavelength has to change. If velocity changes, wavelength changes as well. Okay? It's really important to understand. Okay, and here's a picture of that happening. We've got an inbound light ray right here, okay? It's traveling with this wavelength, the purple wavelength that I've drawn. When it hits this medium, whatever this medium is, you can see that the wavelength is actually changing due to the reality of the speed changing in that other medium, okay? We also know that wavelength is not tied directly to amplitude, so a change in the wavelength does not necessarily mean a change in amplitude. The crests and the troughs remain the same even though the wavelength is changing. Okay? So the fact that the wavelength must change is what causes the light to bend. And this bending of light is what we know as refraction. The definition of refraction, the process by which a light ray bends when it encounters a new medium. Let's look at another interesting phenomenon, okay? I've got a picture here for you. You can see by the purple arrow right here, we've got some incoming light. That light hits a piece of glass. Now we know that glass is a shiny surface, and so some of the light is going to be reflected back out, which is denoted by that dark line, the dark arrow there. But then another portion of the light, which you see down here, is refracted or bent. Okay, so we have incoming light, some of the light is reflected, other light is refracted. Now we know from the first half of the chapter that if you have light that is reflected, the angle that it leaves with is the same angle that it enters with, right? So for what we have here, that would mean that theta 1 equals theta 3. Okay, this is theta 1, this is theta 3. Okay, and those angles are equal. But what about this other angle down here? theta 2. Well, it turns out we have a relationship, which is called Snell's law. And it says this: n1 times the sine of theta 1 equals n2 times the sine of theta 2. Okay, so we know that there's a relationship between the incoming light angle, theta 1, and the refracted light angle theta 2. But what is that relationship? Well, it has to do with this value we call n. And n is defined as the index of refraction. Now, n equals c over v, where c is the speed of light in a vacuum and v is the speed of light in another medium. The speed of light in air is very close to the speed of light in a vacuum. So v, which is the speed of light in the other air, so v in air is very close to c, the speed of light in a vacuum. In fact, we will say they were equal, which would mean that n in air equals 1.00 with 3 significant figures. However, this index of refraction is going to be different as light hits different mediums, okay? Because light generally travels more quickly through air than other more dense mediums, right? That basically tells us that the denominator, v, is typically going to be smaller than the numerator, c, because it's going to travel more slowly through other mediums than it would through a vacuum. And therefore, we are most oftentimes going to have an index of refraction that is greater than 1. And the whole point of having these numbers, and even using Snell's law, is that if we know one index of refraction, we can typically find the other one. If we know both indexes of refraction, we know both n1 and n2, and we know potentially one angle, then we can solve for the other angle. It just allows us to understand the relationship between the speed that the light is traveling with, which is summed up in n, and then how the light bends as it hits the separate mediums. All right, now let's move on and talk a little bit more about lenses. What is a lens? A lens is a specific transparent object through which light can travel. Here's another definition. It is a carefully ground or molded piece of transparent material that refracts light waves in such a way as to form an image. And you looked at two lenses in particular this half of the module. The first one was a converging lens that I've drawn a picture of here. So in a converging lens, what you see is you have light rays that come in and they all meet or converge at one point. That is a converging lens. Now, just like the concave and the convex mirrors that we looked at last time, light rays have very specific ways that they travel through a converging lens. Let's go ahead and look at that. Okay, I've got 3 here for you. The first one is the red line we've got here, and that is when you have light rays that are coming in horizontally. Okay, when light rays come in horizontally into a converging lens, they're going to come out through the focus on the other side. Okay, that's that red line there. Okay, let's look at the blue line down here. If you have light rays that are coming through the focus, my line's a little off, through the focus on the object side, it's going to come out horizontally on the other side of the lens. You can see that too. Oops, I'll recheck that one. And then finally, if you have light rays that travel directly through the center of a lens, there will be no diffraction, no deflection at all. It will just travel straight. Okay? So that's the 3 ways that light rays travel in a converging lens. And you can see here is our image over here. I'm going to undo it because I like the green. That's the image. You can see that the image we have here is a real image. That is, the light rays are actually converging on that side. It is reduced in size and it is inverted. That is how this particular image is formed when light rays travel through a converging lens past an object. Okay. The other type of lens we're going to talk about is a diverging lens, which I have a picture here for you. And what you can see in a diverging lens is that even though all the light rays come in, they actually spread out as they move through the lens. Okay, let me kind of take those off so we don't. And that is the premise of a diverging lens, is that they are spreading out as they travel through the lens. But they also do have predictable ways in which they travel, and let's look at that now. Again, here's our diverging lens down here. Here's our object. It's the green line right here. And we've got three ways in which they travel. The first one is that if we have light rays that are coming in horizontally, they're going to come out as though they came through the focus on the object side. Okay? That's what happens when they come in horizontally. If light rays are traveling toward the focus on the other side, so this is here, it's traveling toward this focus, right? Traveling toward it, it's going to come out horizontally. That's the second path we see. And then again, the third path is that they're going through the center of the image, of the lens, then there'll be no diffraction at all, no deflection, no bending, okay? And then you can see here what we have again by the little green right there. That's our image. And the image for this diverging lens is clearly, it's a virtual image. It is reduced in size, and it is upright. Now that's one thing that's kind of like the opposite between lenses and mirrors. If you remember when we had a mirror, right? When we had a mirror, we had a light ray that came in. If we were extrapolating that on the other side of the mirror, and then the light ray actually did reflect back. That was what we had for mirrors. But for a lens, right, the light rays travel through the lens. So for a lens, any image that's formed on the opposite side from the object is going to be a real image, and anything that's on the same side is going to be a virtual image. Okay, which is what we have here. We have a virtual image. Now, interestingly enough, for the diverging lens, whether the object is located beyond 2F, so out here somewhere, at 2F, between 2F and F, which is what we've got here, or even inside F and the lens, the image is always going to be on the object side of the lens, which is what we have. It's going to be virtual, upright, and reduced. And my question to you is simply, why? Why is that you would have virtual images when you're looking at a diverging lens? Well, the reality is that a diverging lens spreads the light rays in such a way that they do not converge. As they travel through the lens. All right, we're also going to talk a little bit in class about myopia and hyperopia, hopefully, which has to do with nearsightedness and farsightedness. But that's all I have for this lecture, and I will look forward to seeing you all sometime soon.